All right, graph one cycle of the function g of x equals cosecant of pi minus pi times x minus 5 all divided by 3. So to do that, we are going to graph the equation with sine instead of cosecant. I've actually rewritten it here with cosecant, where I've taken the 3 and changed it to 1/3 and negative 5/3. And then I've factored out omega. I'm actually going to call omega negative pi. Well, it's really still just pi because period is a distance, so it's not going to be like a negative period. But this helps us understand that there's a reflection in there, a horizontal reflection. Like if the negative is in the front, it's a vertical reflection, but in the front of x is a horizontal reflection. But I wanted to take that out of here, so I have this as x minus 1, so that I know this graph is moving to the right one. Okay, lots of details. Let's focus on this being sine instead of cosecant to begin with, and then we can just do our magic to turn it into a cosecant. So, one thing to keep in mind that we learned just last week, and that is that since sine, actually, yeah, we just barely learned this in section 2.1, is the fact that if sine is negative, because it's an odd function, sine, here, let's just review this little property here. The sine of negative x is the same as negative sine of x. And that's because it's an odd function. So if you plug in a negative value, you get the opposite function, the opposite y value, right? Plug in a negative x value, you get the opposite y value. That's kind of the idea behind that. And that's our odd identity, or odd property for its symmetry. So because of that, this negative right here can actually be put out here. So then we don't have to deal with it being a horizontal reflection. We can just say it's a vertical reflection over the x-axis instead. I think that makes it a little easier to deal with. So then we have pi times x minus 1 minus 5/3 . So this is the amplitude, right? 1/3 is the amplitude. Pi is omega, so that means the period is going to be 2 pi divided by pi, which is 2. And then this is going to move it to the right one. That's our phase shift. And then this moves it down 5/3. Okay, we're really going to need to focus on our quarter marks on this one. All right, let's put, I'm going to count by twos just because I know there's a lot of halves in this problem. So 2, 4, 6, no, I'm counting by twos. I was going to do ones. I did that wrong. I was going to say this is 1, 2, 3, 4. Maybe I should go even bigger than that to make sure I'm getting, because a period of 2 would mean that this goes up and down in that amount. That seems a little squished. Let's spread it out a little bit more. See, this is why they always tell you to use a pencil in math. 1, 2, 3. That gives us room for our shift to the right and gives us a little bit more breathing room so we can see what's happening. Okay, so sine, if we say, let's label this direction so that this is 1. So this is kind of split into thirds, and the reason for that is that the amplitude is 1/3. Okay, so our sine graph would be here, 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 and here. That would be like our quarter marks, because here's the period of 2, amplitude of 1/3, and we've got our points found at every quarter, right? Okay, what should we do next? We've scaled it vertically, we've scaled it horizontally. Now we need to worry about the shifting, perhaps. So we need to move this whole thing to the right one. I think, yeah, they're all going to move together. So those moving to the right one would be over there. Then we need to move down 5/3. So if you need to, you can think of that as 2 2/3. So this point here at 0 is going to move down to 2 2/3, so about right there. Oh wait, but this is, I didn't label that correctly, did I? And this wouldn't be 2 2/3, it would be 1 2/3. I think I need a nap. So 1 2/3, and that mark right there is actually at -1, because I was counting by threes. Got myself mixed up. Okay, so that's at -1, which means if this is going down 1 2/3, it'll be 5/3, because I broke it up by thirds, so it would be there. So then this point is at 1/3, but it's going to go down 5/3. So 1, 2, 3, 4, 5 to there. And this one is going down to 5/3. This point's going down to 5/3. And this point's going down to 5/3. There. Okay, now I'm going to throw my asymptotes in there. So asymptotes happen where the sine graph crossed the x-axis before we transform base. I usually do those asymptotes before I do that vertical shift. So there those are. So now our cosecant graph should just be able to go in between here and here. That would be one cycle of the graph. Okay, let's kind of list the important values so that even though our graph is a little bit ugly, we can tell where things are located. So this asymptote is at x = 1. We have another one at x = 2 and x = 3. So those are our asymptotes. Can't write. My handwriting's horrible. Okay, so asymptotes, that's what those are. And then the period we already said is 2. And let's figure out the range of our graph, because that'll tell us exactly where those other points are. So our range would go from -infinity up to this point right here at, that was at -5/3, right? And that should be closed interval. And then this one should be Did I go too far with that? I feel like I've done something wrong. Okay, I figured out my mistake. I was counting wrong. So this part right here is actually at -6/3 because it was at -1/3 and then we dropped it another 5/3. And of course -6/3 is just -2. And then this point here is at -4/3. To infinity. So there's our range from -infinity to -2 and -4/3 to infinity. The domain would be all real numbers except for x = 1, 2, 3, 4 integer values, basically k. And we've got the period is 2. I think we've got everything in there. Now, I went ahead and graphed this on Desmos earlier. So let's compare this graph to what I got when I did this on Desmos. I highly recommend Desmos to help you just verify that you're graphing things correctly. So this point here would be in a piece of the graph. No, this is telling me that I've done this wrong. If I moved this to the right, there wouldn't be a piece there. It would have been down here. And then down 5/3. Maybe again I need to look at Desmos closer and figure out what the discrepancy is here. Oh, did I forget to do a reflection? Maybe that's what it is. Remember how I said that this negative, using the odd property, would put the negative out here, which would mean that this has a reflection. I think I forgot to do the reflection. That's where I messed up. So that means, I bet you're already afraid of this assignment for all the mistakes I'm making here. The thing is, you would only have to do like one of these types of problems on a test or something, not a whole assignment's worth. So it's important, though, to practice to make sure you can get these little details. And I don't think you would ever have something this hard on a test. So we need to flip around these points. So this would be down here and this would be up here because of that negative reflection happening. So that would put this here, and this one would be here, which means this one would be here. Let's see if that makes more sense, because I've scaled this weird, right? So this point right here, based on my scaling, would be over a half and down 1 1/3. I think that does match Desmos. So I think the only issue I had when comparing this to Desmos was that I had forgotten to reflect it. I had forgotten about the negative. Because look, all of our minimums and maximums are at negative values. -2, yep, that's a -2 for the bottom restriction of the range. And then the top restriction of the range is at -4/3, -1 1/3. Yep, okay, I believe that matches. This graph looks a lot different than this just because of the way it's been scaled, because these are counting ones, these grids, and on my grids I counted 1 as 3 grid marks. So it makes this look a lot squished vertically than this one does. But it makes sense that it looks more squished vertically because that's what that 1/3 is doing, is squishing it, compressing it vertically. Like I said,